Okay, I think let's start out. So we're going to switch the chapter. Of course, chapter 5 has a lot of preliminaries and examples, and I hope you've gone through a lot of them. And so, obviously, you know I like hierarchical structures. So those are the problems I kind of dwelled on. Those were the complicated problems in your homework. So kudos on getting through it all. But be responsible for like the CLT proof or the delta method proof. I'm going to pick something like that on the midterm. Okay, so you'll ask me, is there going to be any sort of proof? Yeah, I'll do one of them with like a Taylor extension. So, think so. New homework is out. This is comparing delta, base, and boot strapped to each other. So the name of the game in this problem, and it walks you through in a lot of steps. I think there's like a 3 or 4 page write-up. I ended up writing down that it was due on Friday, March 13th, but that's of course spring break. So we'll always push to the next time class meets if I do that. I'll change it on. But Monday, March 16th. I will warn you, you need to start this early. So because what's going to happen is you have a midterm right after that, and you've got another set of homework that's going to be due. I would take this week to start on this thing. So carve one of them out. Get the simulation code up and running. And so otherwise, you're going to get this avalanche come this date. So delta, base, and boot, you're going to try to estimate this parameter. It's just a function of p. And you get to observe these xi's. And there's 10 of them. So what I'm going to have you do is I'm going to have you compare these 3 procedures for different configurations of n and p. So n might be something like this: 10, 20, 50, and p might be 0.1, 0.5, 0.9. Now I have a lot more configurations than that on the homework. But what this would say is you've got 3 times 3 different sets of simulations that you're going to run for each one of these methods. So 3 times 3 times 3, 27 things that you're doing. I actually have more n and more p. So it's quite a few comparisons. I want you to compare the performance for lots of n's and lots of p's. And what you're going to do is you're going to sample from this for a configuration of n and p, see how well you do, and you're going to do it again and again and again and again and again and again. So you get an idea of how the method works for a particular comparison of n and p. And then you're going to iterate through to another n-p combination. So I think there's 28 combos in the homework that I laid out, all conceptually the same. So one of the difficulties in this homework assignment is summarizing your results. So you're going to need a good graphic. I don't want a table of all this stuff, so I need a graphic. And I want you to ultimately estimate means and variances of things. So what's the mean of this distribution for whatever you're estimating things with? You're going to compute x bar in like the bootstrap thing, and you're going to plug in x bar for p. You're going to be doing the same sort of thing in the delta method as well. That's going to be your mean, but your variance is computed differently. And so what I'm going to have you do first is look at the delta method. I'm going to pick some n and some p. You're going to try this experiment once. You're going to create the bootstrap distribution of this statistic. You're going to do the delta method distribution. You're going to compare them to each other. So see if they overlay each other. Know what the truth is. And so that'll just kind of convince you things work. And then you're going to get underway to do a lot of comparisons. There are pitfalls. So this is not a smooth assignment. I made this a real problem. So real problems, there's always choices that need to be made. So you're going to have to invoke your own decision making. And so if you're studying the means or something like this, if you're doing delta method, it is a mean and variance driven thing. You can't get away from it. So let's imagine I see all ones in everything. Delta method fails. It's going to fail. So you need to report how often it fails. And when it's okay, how well is it? But how would you kind of consider that case in practice? I would say it's not a good technique. It fails a lot. So as you're doing this over and over and over and over again, you need to somehow account for how often it fails. So I want you to report something about that. People are always like, what do you want to report? usually report like the box plots of the averages or something like that, and then talk about how many times it failed. They'll also say some fraction of the time it actually worked. And here was the bootstrap distribution. What does the bootstrap theory say about that sort of stuff? It says nothing. It doesn't account for it. And so if you just take away your failures and throw them away, you're not really doing the bootstrap. Something else, you're truncating things. And the repercussions of that can be severe. Delta method, mean won't exist, same problem. Bootstrap, mean won't exist, same problem. What about Bayes? So you're going to get some distribution. So you'll take your beta distribution and you'll transform it. I told you last time the transformed beta distribution into the odds. It's called a beta prime distribution. That's a lot of knowledge. You could go to Wikipedia and look up what the beta prime distribution is. You could see how its expectation and variance are computed. So you don't actually have to do them by hand. You don't have to simulate them. It costs you a lot of simulation time. What you'll find out is that sometimes the mean and the variance, when n is small, don't exist. Does that mean Bayes failed? If I ask you to report means and variances for bootstrap and for delta method, it makes sense to do that because you just have this in, for the delta method, it's all about means and variances. For the bootstrap, you just have these empirical things. Averaging. For Bayes, what you get back is a distribution. The Bayes answer is a full distribution, and it's a bit overloaded. And so if a mean didn't exist, you could compute something different. So I don't think that means Bayes fails. Now you could change the hyperparameters and make it so the mean always existed. I don't like that idea because you're going to put a lot of bias into things if you do it. But you can experiment with all those things. Advocate something. I would report the posterior mode. Call that the maximum a posteriori estimate. But it's just the mode, the high point. That exists, and I can compute intervals in a different way. I don't have to be variance driven. That's what I like about Bayes. Is I get a full distribution. If the mean doesn't exist, and we've seen in homework problems the mean not existing, that's just a mathematical consequence of what the arithmetic mean is. It's not always a good summary, especially when it doesn't exist. It's not a good measure of the center because it doesn't exist, but you can always use mode. So something exists in this distribution. So I'm going to make you invoke your choices in those cases where it fails. On Thursday, we can talk about this if you want. We'll do a review session. You guys want to show up, catch up? All questions are open. I know I don't have problems for you, but I will in a couple days put up chapter 6 problems as well. We have a bunch of problems to work. But even if you want to get started early or go over some of chapter 5 problems, you can take advantage of that. Or you can take the time and launch this. Get it coded up while you sit there and watch my review session. It won't be instant. But start early on this, because this one will nip you. So real quickly, if you wait. Any questions? So, switching the chapter, the sufficiency principle. Sufficiency principle says this. This is the principle. If Tx is a sufficient statistic, then any inferences about theta should only depend on x through T of x. Okay. So that's a pretty convoluted statement. What is that? It's a little hard to digest. I'll say something else that the book says in a second, but really any function T of x, let's just let this be an arbitrary statistic, is a form of data reduction. Okay, so if I have a vector of data and I compute the average, I've just reduced the data from an n-dimensional thing to a one-dimensional thing. And so it's a form of summary of theta maybe. So in the case of the mean, x bar is maybe a good summary for the mean in a normal distribution. And it is. So that's the one I would go after. And so the question is how far can we reduce all the data and still have the information about theta? And so in one of the questions might be also how much information do we want to retain about data? And there's a whole bunch of data reduction, dimension reduction techniques that you lose information, but maybe you only lose a little bit. A sufficient statistic is set up so that you don't lose anything. So you reduce the data and you lose no information about data. So let's imagine for a second. Somebody walks in with a vector of data and tells you that it's normally distributed and says that I've got a really big vector of data. It turns out that it's 42 million quintillion raised to the terabillion, if that's a number, bytes. So I'm going to try to load this into a database. And you as a statistician say pause for a second. You might say, I would do something different. What would you do? So you're going to blow up the database. Or you can do something different. What would you do? They want to know about the mean of a normal distribution. They say it's normally distributed, and they have so many bytes of information that it blows out all of Virginia Tech's databases. So you might say you don't need to store that whole vector of data. All you have to store is X bar. Why don't you just compute X bar real quick, and then store that. Good solution? What's the assumption? David says no. What's the assumption?
I would say no because to compute X bar, you have to load it in anyway.
Yeah, that's true. So, but you don't have to keep storing it forever. And so you have to load it somewhere and compute it. I could probably solve this using Amazon Web Services, hand it a little bit of the data at a time, compute averages, and have it throw the data, all the little averages back at me. So I can do this in a parallel distributed fashion, and then I average all those X bars. So maybe I could do that. So, but I don't want to hold on to this data forever because I've got the sufficient compression, X bar. There is an assumption though. The assumption is that that data was normally distributed in the first place. That you trusted them and believed them. So sufficiency is a concept of data with model in tow. So you know it came from that model. Now I can talk about that all day long on the blackboard. We can discuss that all day long in all our problems, but in reality, you get data and you don't know. And so if you knew what the model was, then you can just store the sufficient stuff. If you aren't sure, you better hold on. So sufficiency is a model-based concept, not just a database concept. So I think that's important. Sufficient statistics don't lose any information. So one sufficient statistic, it's not much of a compression, is X itself. So the data itself is sufficient. Follows this definition. So all my inferences about theta come through, only depend on X through X. Isomorphism. A is equal to A, tautology. Simple logic. Okay, so X itself is sufficient. Later on, we're going to be asking how far can we compress things. So that's what's called minimal sufficient, and we'll get into that. Let me just show you an example. Real quickly. So consider xi's coming from a Bernoulli distribution with parameter p, and I get n data points. So the joint distribution, f of x, given p, this is just x1 to xn because I'm presupposing everything I say is IID without mention of it, albeit I keep mentioning it. It's all IID stuff. This is just the product. I goes from 1 to n of all of its sampling distributions. Bless you. This is just fxi. Given. My xi's are encoded in the traditional fashion, a 1 and a 0. So the 1 happens with probability p, and the 0 happens with probability 1. And so I could write this down, and I've got an expression where p depends on x, and I need to put in all of the x's. Or I can simplify this. Sum of the xi. This is n minus sum of the xi's. So I'll just point out, this is the sufficient thing. And so I don't need to know all of the xi's to compute this function. Because I can write it down in a reduced form, I only need to know the sum of the xi's. So my inferences on p only depend on the xi's through that function. So it doesn't matter the order I solve 1s and 0s, there's no information there if this was all IID. I don't need to know where they all laid, where they came up. All I need to know is what that sum is. So that's what this definition is talking about. So this is also a minimal sufficient statistic because I can't compress it. We'll come up with a technical definition and a way you can mathematically verify that very soon. But there is a mathematical way of quantifying this statement. So let me just write down what the book says. The book says if px given px and theta is equal to a constant, then px is sufficient. And this is really an if and only if statement as well. It goes in both directions. So if this distribution is a constant, and tx is sufficient. If tx is sufficient, that thing will be a constant. So this is what the book says. That's constant, tx is sufficient. And I stared at that when I was taking grad inference a few years ago. I looked at that. I couldn't make any sense of this.
Suppose you have a uniform distribution which is never just constant whether you have tx or not. So does that apply in this sense?
All of them. This will be a universal concept.
So in case you have a uniform distribution which is constant, so in that case what do you think, who do you think px will be?
So it depends on what theta is. So what's your theta in all of this? Is it boundaries? So if I let those be unknown, so you have to tell me theta and I'll tell you what tx is. But we have to define theta first. So maybe in the case where theta is the maximum, the sufficient statistic turns out to be the maximum.
No, my question was, so you have a uniform distribution which is constant. So no matter what your tx is, anyways it's going to remain constant.
I see what you're saying. This is a constant that does not depend on theta. Let me be real clear about it. I get your question. Does not depend on theta. So let me write it down a different way. P x given tx and beta is equal to px given tx. Very good. I didn't say constant with respect to what. And so you invoked a different mindset on what I mean by constant. So I mean not a function of theta. So I can compute this probability distribution, and no thetas will appear in the formula. It's a different way of saying that. So, and I did stare at this for quite a long time, and okay, why is that? Anybody have a good explanation of this? So the book kind of just says this. And it's done, and it uses this in a bunch of proofs. And knowing this, I can do the proof, showing that tx and x have the same amount of information in them. So one way of saying this again is tx and x have the same information about theta if this probability distribution is a constant with respect to theta. It's interesting. So we must have somebody that studied undergraduate statistics. Now granted, when I went to grad school and took grad inference, I didn't have undergrad inference. I had never seen this concept before. It was brand new to me. But everybody else seemed to understand what a sufficient statistic was. I think we can kind of understand it through this example. If there's a compression, it's the same formula. But no explanations? Okay, let me try to explain it. I think the key is understanding what that function actually is. So, what exactly is px given tx and beta? I think that's going to answer the question. If I understand what that function even represents, what that probability distribution is, then maybe I can come up with this. How do you compute this? If I gave you a distribution with x, so I'm going to give you this. So you get same stuff you always get in this class. Xi's are the little pxi's beta. I'll just say get this. It's not invoke independence. We don't need independence for this. So let's just say you get to know px given beta. So you get that function. You get the data. And you get a mechanism for generating the data. So again, this is model and tow. So I'm giving you theoretical stuff. That if you knew the sampling distribution, I can say a whole bunch of stuff. What do we do in practice? We get data, we model it, we say, oh, this is the sampling distribution. So it's still a useful concept, though. The reason I still like this concept is because of computing. I'll think more about that when we get through the theory. Mohammed.
So I'm a bit confused about something. So is this saying that the information you get from your parameters can always be expressed through some function of the data or the population?
Well, the parameters can always be expressed through some theta or the population. Data can be inferred from t of x or x, and I don't lose any info. That's what I'm saying.
But what if data is something like the shape parameter for the gamma distribution? Can you get that?
I can learn anything. If the parameters are identified in a distribution, I can learn it. But yeah, no problem. You can generate your gamma data, bring it to me, and I'll allow you. So, can I write it down as a very reduced form is a different question. So can I compress all of the data into something one-dimensional for alpha and beta? The answer there is going to be much more complicated. So, but if you give me x, the sufficient statistic, a sufficient statistic, I'll do it. And soon I'll show you how to do it. Some other question? But if Tx is sufficient, then I can learn just about those parameters just as well as using the whole vector. That's what this concept's about. So you get to know the sampling distribution. How do you compute this?
Distribution for T of X.
Yeah, you can find the distribution for T of X and do what with it? So find T of X given theta. This is a transform. So you give me X, I guess I can do that. I convince myself in my mind I can do that. I can always do it. Can I do the math and write it down analytically? I don't know. But it exists, and I can do it. Doable. Maybe only conceptually. Computationally, it can always be done. But X is random, so T of X is random. It has a distribution. What do I do with this now? Compute this. Get this. David said, that means you also get that. What do I do with those two functions? I get this.
Px over Ptx.
That's it. That's it. Divided by each other. So let me just be real clear about this. This right here, I'm going to take Px and divide by Ptx. This is correct. I'm going to be a little bit more clear about this. This is because Px, Tx, the joint distribution is just P of X. So if I have the joint and I divide by the margin, that's the conditional. So nothing up my sleeve. But these are equal to each other. There's no extra information in T of X if I get X. I can compute it for free. Don't learn anything extra. So you give me X, I've got T of X. Trivially, it doesn't change the probability distribution. Probability statements are equal. They're governed by the probability distribution of X. T of X is just a computation, a calculation, we should say. So it's just the ratio of these two things. And so when I look at this, I get it. Now I get it. For this thing to be a constant, what it means is that the shapes of these two things are exactly the same as a function of theta. So if I move theta around, if this thing is a constant, it means that these two functions are behaving exactly the same as a function of theta. That means they have the same information about theta. So let me just write that down. Dx given Tx theta is equal to Tx given theta over Ptx given theta is equal to a constant. Flush it in terms of theta. So not a function of theta. This thing right here is just Px dx. Means both numerator and denominator have the same shape. So the same information about theta. Show you our example. Let's go back to the Bernoulli example. Xi's come from a Bernoulli. Parameter p, I goes from 1 to n. Same setup. We know what px is. Is equal to product. I goes from 1 to n. Pxi. 1 minus pxi. P sum of the xi's. 1 minus p n minus sum of the xi's. Same thing as others. And I've said, just by kind of looking at this thing, I think that's sufficient. I'm actually doing the factorization theorem in my head. We're going to learn about that soon. The factorization theorem says. That's kind of your utility for figuring out what the sufficient statistics are. Saying that, I was really impressed with myself in graduate school because when I looked at this, I figured out in my head what the factorization theorem said. So, oh, I see if it factors like this. So I thought I was brilliant, but it's actually a pretty trivial thing to notice. We'll talk about that formally next time, I think. But I write this down, and we think sum of the xi's is sufficient. It is. We're going to verify this by going back to this definition. So if you want to verify something's sufficient, I just go back to this ratio and show that it's constant with respect to my parameters. The parameters in this case are p. That's my theta. And so I need to figure out what the distribution of that is. And everybody knows already. So what's p tx? I know everybody knows. So binomial, I'll just say it. So I've taken the thunder. So this is a binomial distribution. So the sum of the xi's, and in Stat 101 they taught you how to construct this distribution. So they say it's the number of successes. So this is the number of ones and everything. So what's the probability of observing those? Well, it's p to the raised to the number of times it occurred. How many failures did I see? N minus sum of the xi's. Each one of those occurred with probability 1 minus p, so I product those together. Those are just the probabilities of ones and zeros in a vector. But because the order doesn't mean anything, I have to take out all the possible orderings. So this is the binomial coefficient. N factorial over sum of the xi's factorial n minus some of the xi's. So in your probability class, it said there's n permutations of all of the data, and I can exchange all of the ones in that number of ways, and all of the zeros in that number of ways, so I'm going to divide that out of the number of combinations. Switch around the ones, and I can't tell the vector apart from each other. So this looks almost like this function over here, but it's off by the normalizing constant. So this function is a function of p. Looks a heck of a lot like that function. It's a function of p, except it's raised by that. So p of x, and let me write this down as p right here. My theta is p in this equation, over p of x, given p is equal to 1 over and choose some of the xi's. An obvious thing to notice is this is not a function of p. So it's like I've got these two curves right here. It's a function of p. These live between 0 and 1. So they do something. One is raised. They're supposed to have exactly the same shape. So this distance is just this common factor right here. So now I can see. I can understand what they're talking about, that if this thing is a constant, then Tx is sufficient, really taking two distributions and dividing them by each other.
So both are probability distributions, right?
That's right.
So shouldn't they both sum to 1? So shouldn't there just never be a constant? Shouldn't it always just go to 1?
I have an counterexample right there.
I know.
I'm not summing them. I'm just taking the mass functions and dividing them by each other.
But how can one be consistently lower than the other one and they both sum to 1?
So I'm plugging in x right here, so there's only one x in this stuff. I'm not summing over all combinations of x. So I'm not summing over all things I didn't see. So it's really the way I think about this. I apologize to all the classicists out there, and I'm really taking the ratio of likelihood functions and dividing them by each other. The likelihood principle falls out of this. Something called the conditionality principle.
And that's always going to be the integration constant on the bottom.
Pretty much. Let's look at a different example in a moment. But I will say what this is, but it is the ratio of the integrating constants, but it can have some x's in it. So be careful, that's what I want you to be aware of. But yeah, it is. It's the normalizing constant difference. Let's just go with that, yes.
Well, is the sufficient statistic always going to be one-dimensional?
No. So let me give you a counterexample real quick, Hoshi. So a good counterexample to everything. You're never going to be able to compress that stuff. Don't use x bar, because you're estimating something that doesn't even exist in the distribution. Does anybody know what the distribution of x bar is from a Cauchy distribution? Cauchy, same Cauchy. So Cauchy 0, 1, if I average it all together, Cauchy 0, 1. You never get this compression of variance. Amazing. That's in the book. So what distribution is this? So remember, let's just look at what this is. Right here, this is P of x given T of x. So this is a distribution over these xi's. Given that everything that I plug in right here sum of the xi's is fixed. So this is a distribution over all the combinations of ones and zeros such that the sum of the xi's is fixed. The number of ones is constant. So just conceptualize what this distribution is. Like my bar, it always means that's fixed. So, and it's saying this distribution is uniformly distributed over all those combinations. And so how many combinations are there of those things? A number. So this is just a uniform distribution over all the combinations of ones and zeros such that they sum the sum of the xi's. So I guess that's cool. I want to ask you, could you sample from this distribution if I asked you to? You can definitely sample from a Bernoulli, which is coin flipping. You could draw a uniform, you could do it. So you could sample binomials as well, no problem. Transformation of that thing. Could you sample this? Pretty easily, right? How would you do it?
Fix it to the number of success. You can choose, assume you have n sample, then you fix k success, and take like k place in the place.
Just do it. I think it's what he said. Just take all those vectors, throw them into a hat, give it a stir, and pull one out. Give it a stir, pull one out. Put them back in, of course. Sample with displacement. I think that's it. You just do it. How do you sample from a uniform distribution? That's really what the question is. And so, when we go through the proof on the sufficiency principle that x and t of x have the same amount of information, they invoke the notion that you can always sample from this distribution. And that might be something that's hard for you to do in practice. But I'm going to try to convince you in this class you can always sample from anything. So it's an insight you should have. I remember thinking when I was reading through the proof, how do you do it in general? So there is a problem in the book. It shows that x bar is sufficient in a normal distribution. I want to go through that problem next time. I want to go through the proof quickly, then I want to go to that problem, and then I want to come back and talk about the proof just one more time. Okay? To show you what you need to think about to sample from different distributions, maybe looking at an example would be useful. So let's try to do the proof quickly. We'll look at an example and then do the proof slowly. Okay, so here's the proof. Let's just write out the whole thing. So here's what the book says. Question. There's two experimenters. Experimenter 1 and 2. There are two people. Question. Experimenter 1 gets to see x. Experimenter 2 gets to see tx. And the proof argues that both of these experimenters have the exact same information about theta. Remember, this is model in hand. You get model in hand. Everybody gets the model. So everyone gets the model. No mysteries. No notion of sufficiency without model. And the proof goes on to argue that they have the same information. And they argue for a paragraph, and then they show you some math. Let's go through their math. So, experimenter 1. Gets this thing. Oh, and they also get to see the actual realization. I'll be real clear about this. This is the random variable. This is the instance, what they actually see. So random variable and the actual data. So different notation. It's not a vector of a whole bunch of x's. This is an instance in some space.
Are we assuming T that's sufficient?
Yes. Absolutely critical. And you'll see it improved too. We'll invoke that. So, experimenter 1 knows that. Get the model, they can plug this thing in. Plug in x. So, no big deal. This is p of x is equal to little x, the instance. And experimenter 1 can also compute this. No problem. It's just a calculation. This is a true statement. It's just an obviously true probability statement. This knocks this up to a random variable. Here's sufficiency. All I did is I removed theta right there. So thank you so much for telling us T had a special property. T has that property. No dependence on theta. Now here's the trick in the proof. This is the part where I have to convince myself that experimenter 2 can do something. Experimenter 2 can't see actual little x. But experimenter 2 gets to see cap tx. Experimenter 2 has the ability, this is the part I didn't get, to generate new data conditional on tx. And they can simulate from that. So experimenter 2 can do this. Question. I have a constraint on x. I have a constraint on x. It's what the sufficient compression was. And experimenter 2 can draw from this distribution. So this is experimenter 2's random variable. This is the part that confuses everyone in this group. And the argument is that experimenter 2 can draw x's with some probability distribution, and they can capture this x with the same probability. Experimenter 2. Doesn't actually get to see it, but can make a probability statement about it. And that has to do with being able to draw samples from this distribution. So they can draw a new auxiliary set such that this condition is true. They can make a probability statement about it. I didn't change anything here. After unfolding this proof, we get this at the end of the day. after wrapping this up using the definition of a sufficient statistic, retucking theta in there, and then combining this product. So you're going to see this is equal to that. Experimenter 2 can draw new x's and make probability statements about it. I didn't quite get that. It's like, how do you do that? So it turns out you can always do it. In our example with the binomial, experimenter 2 would go and draw a new vector of data of ones and zeros from that uniform distribution. So they would shuffle the hat and pull out a new vector. And that has the same probability distribution as the original thing. Okay, so through an example, we can kind of see that you can draw. Let's look at the normal example for next time for inferring what mu is. And I'm going to ask you the question, how do you sample from that distribution that they have there? You're probably going to say, I don't know. I want to talk about it for a moment. So let's come back, look at another example, and then talk about this line of the proof. So this is where all the action happens. Thanks, you guys. That's it for now.